Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good evening, ladies and gentlemen. Welcome to our lecture. This lecture is sponsored by Technical Society. Talk about what's hot, what's best, what's going on in this industry. And so we are so delighted to have Dr. Li Deng with us tonight. And Li is our Engineer of the Year this year, 2015, for Region 6. And you will be amazed how much he has achieved. And he has 60 patents, international patents, 4 books, and 300 more to 400 papers, technical papers, referee papers. And he has a lot of honors and awards. He's 2013 IEEE SPS Best Paper Award, Editor-in-Chief, IEEE Transaction Audio, Speech, and Language Processing, Editor-in-Chief, IEEE Signal Processing Magazines, Technology Transfer Award, Gold Star Award, 2011 IEEE SPS Meritorious Service Award, General Chair, 2013 IEEE International Conference on Acoustic Speech and Signal Processing, and Board of Governors of IEEE Signal Processing Society, Board of Governor and Vice President of Industrial Relations, Asia Pacific Signal and Information Processing Association, Publication Board, IEEE Signal Processing Society, keynote speaker, Interspeech, September 18, 2014. And he's a keynote speaker at 12th China National Conference on Computational Linguistics. And so many keynotes, I just don't want to say it anymore. And then he's is just amazing person. And so I think you will enjoy it this evening. Thank you.
Thank you very much for the introduction earlier before you came. Yeah. Okay, so today's topic, actually, I originally put the topic called recent advances of deep learning. So many of my colleagues said that, well, I should take opportunity to talk about not only the recent advances, but also maybe some history of how Microsoft got into this area of the research. And this is a very hot area now. People talk about artificial intelligence, machine learning, deep learning. Almost every single day, you get news coming out from the media. So that happened actually over the last 3 or 4 years, maybe 2 or 3 years. So the more recent ones, you get a lot of acquisition, small company acquisition. Microsoft doesn't acquire any, hasn't acquired any company on this. Google acquired quite a lot of companies in this area. So going through this lecture, you are going to see why. Okay. So I'm going to provide a selective overview of a whole bunch of projects done at Microsoft for deep learning. I'm going to show you exactly historically how deep learning got started from here, and how it was advanced, and then how the whole industry actually is working in this area now in terms of state of the art. So I first want to acknowledge many of my colleagues at our deep learning center and Microsoft Research, and also with collaborating universities and many of Microsoft engineering groups. Some of them are probably sitting here, who collaborate with us to create some impact of some project. So almost all the material I will talk about today are public. Okay, we either put those in the CNN or in New York Times. All this. This is called a summary of a whole bunch of things that we put together. And I'm going to point you to some of the new activities we are planning to do. Not much detail because they are not public yet, but I'm going to say whatever I feel comfortable about saying. Okay, so first of all, the first little topic is the how and when and why Microsoft got into deep learning, and I will start with the deep speech recognition. So this is actually very early work that we started doing with academic pioneers. So for example, there's no laser printer here. Okay, but it's okay. So I probably can just talk about this. So officially, Microsoft got into deep learning research approximately towards the end of 2009. So we work with Professor Jeff Hinton at University of Toronto. Actually, the collaboration started earlier than this. We actually worked, right before this one. He traveled to this building, actually in my office. We worked together on this, in this what's called the deep learning for speech recognition. And that, so actually, there's a long story about how it led to this workshop. So during the workshop, there was extremely high interest in doing deep learning for speech recognition. And then he consulted with from university academic research coming over here, and we learned a great deal from them. And then later on, he sent a couple of students to work with us. So we devoted a very fair amount of resource into the collaboration, and then we actually make the whole thing work well. So now every single voice interaction system in the world, fair to say, including Microsoft, Google's, Amazon's, is using this technology. So I'm going to tell you how this whole thing started, as part of the presentation. So the track. So we started, doing somewhere around 2009, and we worked quite a number of years, in collaboration with academic, and most of the work done is right in this building. And we created this technology called the deep learning speech recognition. That was first time demoed by my boss, Zheng You's boss, our boss, Rick Rashid. Now he retired after he gave this talk. Soon after he gave this talk, he was actually in China giving this talk, and then that story was featured in New York Times in 2012. And John Markov was the reporter, and he interviewed me right in this building, and as well as with Jeff Hinton. And then the story is very amazing. And this is the real-time demo system where Rick Rashid spoke English. He doesn't speak Chinese, and then it's automatically recognized in English and gets translated into Chinese, and using Chinese language synthesizer to speak it out. And it sounds like him. So, so many of you, our college went over there, and then people saw that, students, this is a big student of 3,000 people, students, and then they shed tears. They say, wow, now they can talk with their mother-in-law easily. This is a joke, right? A lot of Western people, they marry with Japanese, they couldn't speak with their, mother-in-law, and now they were able to speak without any difficulty. And that happens in 2012. So now the underlying technology used in this demo actually is what's called deep neural network. So we call it context-dependent deep neural network, or hidden markov. Those are all technical words, and they were invented about 2 years ago, through our collaboration with University of Toronto. And this is the very important figure here. So this is a number of years. So if you sit in back, you want to see that. That's 1999, and this is 2012. So that's about that time. Okay. So this is the a speech recognition error rate. So in 1993, when people started evaluating this word error rate for spontaneous speech recognition, just like the one I'm talking about, error is 100% almost. Everything is wrong. 2019, that's about 20 years ago. And then people are working very hard. So every single year, the error drops. Look at how much people, so this kind of evaluation was sponsored by DARPA. DARPA, they put tons of money to individual group, including companies. IBM is one of them. Many universities participated, and then whoever got the best result, they got funding next year. It's a very stressful test. So if they're not doing well, they get cut off. So that's why it drops so much. So every single year it comes down here. Now roughly about 2000, things don't do much. They don't change anymore. So error stayed the same, about 20-some% of error. Okay, so it's actually stayed about the same for 10 years. So in 2009 and 2010, so when we first started doing deep learning in collaboration with Toronto, error rate dropped from like 20-something to 15-some%. And then for Rick Rush's demo, that was 2 years after that, and that error dropped about 7%. And every time, most of the things he said got recognized correctly. Look at how much it moved from here to here. 10 years, it's just dropping down here. It's essentially the error dropped more than half for this. So this became usable, okay? And the underlying technology, I don't have time to go through all the technical detail about how this deep learning actually work here, except to let you know that the deep learning essentially is to extract speech information and put them into layer by layer representation in the neural network. At the end, we use about up to 12, 13 layers.
Can you give a basic definition of DNN? Is deep learning the same as deep neural nets?
Okay, so for this talk, maybe you can think about it that way. Okay, but so deep neural network is in speech recognition, maybe 90% of the work is done by deep neural network, and there are some additional new advancement of deep learning, like a recurrent neural network, like a memory network, like a deep generative model, like also convolutional net, which are a little bit different from DNA. So think about DNA to be maybe 70%, 60% of deep learning, okay? And the other ones, I don't have time to go through. Well, in the image recognition, I probably say a few words about somewhat different type of network, but they follow similar structure. So the feature that you have layer by layer representation and having the information from bottom up all the way to, to the high level to allow you to do very effective discrimination, pattern recognition, which is the same, okay? So now for ImageNet, I'm going to go through later on. The number of layers goes to about 60 layers. It's amazing. People just keep getting better and better results. And speech, roughly 10 to 15 layers are good enough. But if you have one single layer, you hardly get any good result. So that's the main advance achieved by Microsoft Research during about this year. And that led to, so in 2013, MIT Technology Review, this is a very reputable technology journal, they put deep learning to be top one out of 10 breakthrough technologies. And one of the reasons they put deep learning to be here precisely is because they cited this translation speech in real time from our boss, Rick Rush's demo. So that's a very influential during the time. That's 2012 and 2013. So now I want to tell you a little bit about how this invention gets spread out into the entire industry. Now, Amazon is doing that. Amazon is pretty late. They hire a few people from our group. Google, so Professor Jeff Hinton is one, I have to credit him a great deal. I mean, he's a really pioneer from university. Now, Google acquired his company without actually coming, just one himself and two students. That happened in about 2013. And we are trying to do that as well. We didn't be high enough. But anyway, so there are a lot of interesting stories. I'm going to, and he's the one who actually get together with all the 10 authors, including IBM people, Google people, and then his graduate student and myself and my colleagues, and together to write up this paper. So this paper, just about 2 years ago, we get about 600 citations, a very, very highly cited paper. Essentially, it becomes sort of the state-of-the-art for this. So he managed to get it's called the four shared views of 4 research groups, including Google. So this is the only time competitors get together without patent fight, right? And then without any argument. We all agree on every single word we wrote. It's about 20 pages of paper, So we are coordinating. Actually, he and I actually spent a lot of time coordinating all this. Everybody, happy about the conclusions. Exactly. So this one become very interesting kind of original paper that many people follow up. And then, of course, so once you do that, the large scale speech recognition successfully, and everybody follow, right? And that includes Google now. That's our Skype translator, Windows Phone, Xbox. All the voice here is using the same technology I show you. The Siri, they're using that. My boss got hired by Apple about 2 years ago, starting doing all this. And then this is Baidu. Basically, all single company, major companies, they are using the same technology. So this is very, very impactful. And also university labs and DARPA program now, every single team in their group, they use that technology. So this is and I'm very proud to say that technology originally started in this building, right on the 3rd floor here. Okay, so this is the article from Business Week. Everybody know about it. So the race to buy human brain behind deep learning machine, and that was about 1 year ago. So our new boss, Peter Lee, actually mentioned some very interesting work here. This is a fabulous article that I used to recruit people. Okay? So he said, according to him, my boss. Okay, so I actually checked with him whether he really meant that. He told me he's kind of. So including Microsoft, Google. So Google actually spent about $400 million to purchase this company about 1 year ago, and we didn't do that. He said that the Google find themselves in a battle for the talents. Microsoft has gone from 4 full-time employees, about 4 people that were working together about in the time that I talk about, going to about 70 about 1 year ago. So now it's more, right? And maybe about 100 some people in the company. Maybe some of you are here. And we would have more if talent there were to be had. And last year, the cost of top deep learning expert was about the same as top NFL quarterback prospect. Do you know how much they make? So I didn't get an answer from this. Well, that's our boss there, right? So I'm not sure. Anyway, so this is a very good recruiting statement. And he put it in Business Week, so I can quote them. Okay, so now I'm going to go, so this is not just speech recognition. Speech is the beginning, right? So now we are moving from recognition to do translation, to do understanding. So I'm going to spend 3 minutes talking about each of the project at a high level. Okay, now for the speech translation project, we have this, the Wire cover this story, and the CNN cover this story, all within 1 year. So we talk about how the Skype use the artificial intelligence and deep learning to build the new language. I do have video, so if I have time, I'm going to show you some of the video how this technology works. Now, we also have this speech understanding task, which is used in, so recognition is not the whole story, right? You have to understand that for the Siri to be able to talk with you, and for Cortana to be able to talk to Google now. They all use the technology called the speech understanding. But now, so this is one of the very popular model. This is a little bit different than a deep neural network. It has a recurrent characteristic. So the time becomes the layer in this type of architecture. And it's very, very useful for any time series problems, like speech translation, understanding, and also for something like time series analysis. I read some paper, people using this model to do stock market prediction, but haven't seen. But even if they use that successfully, I don't think they're going to publish anything. Otherwise, they are going to because it's kind of competitive, But recognition is, it's not competitive, right? Everybody can get a gain out of it, right? So you have to be careful. So we wrote some paper on this. So next topic, I'm going to do very quick. But so many projects I want to go, so I'm going to selectively go through some of those. So the next, this is a big subject called the deep image recognition at Microsoft, and Microsoft is the latecomer for this area. So I have some very interesting story to tell you how this whole thing started. So in the fall of 2012, it's the same thing for image recognition. It's the same, very similar to speech, except the history will be shorter. And also, it's not government that sponsored the competition, but the Stanford University actually sponsored that. Well, they don't sponsor; they create a database to evaluate people's, different teams' competition. So before 2012, people used this task called the ImageNet. So so it's about 1,000 categories of images. So the purpose is that they give you about 1 million samples. They train them. Everybody train their Firebase system. Right? Before 2012, they're all shallow system. Essentially, they do handcraft feature engineering. They use SVM. They use sparse, classifier. Just one single classifier, based upon the handcrafted features to do that. And everybody's doing that. And these are the typical error rate, about 26%. And that has been staying for about last several years. So ever since the competition was created, that's about 3 or 4 years, about maybe 5 years ago. The first 2 or 3 years, error also keep dropping. Now up until this time, I think the previous year, 2011, also error rate is about 20-some%. It's about, rather than in speech, you get 10 years of stable error. They got about 26% over here to 2 or 3 years. And then in the same year over here, this is Toronto's group by the same Professor Jeff Hinton, his group. And they actually knew that speech works, right? That was about 2 years after that. And essentially, if you have the belief that technology is good, and he put the best people in his team, to apply the same technology using convolutional network. It's a bit different than deep network, but similar kind of concept. Many layers. And at that time, there is 7 layers. And all of a sudden, they dropped error from 26 to 15%, just like speech recognition. And that created a huge amount of excitement. So what I want to say over here is that, so during the fall 2012, October 20th or somewhere, is about October, and the announcement of the result was made public. Typically, the way they do competition is that people submit the result, and Stanford University, they evaluate. You have no idea how well you do because the test set is withheld by them. Right? So when the result was actually announced, this is so good. Many people don't believe it. So on the day when the result was announced, I was actually here together in this room, in the very room, having the lecture on machine learning. There is also Chris Bishop, some of our very famous, scientists in our company. We are doing actually company-wide machine learning lecture. I was one of the lecturers. So right before I give the lecture, so I got an email. I got an email from my cell phone, and Jeff Hinton sent an email to me saying, "Lee, take a look. Look at how much margin it is, to go from here." And then I wasn't sure how genuine it is, right? So I sent that to the company, all these people doing computer vision, and they come back and said, "Oh, there must be something wrong with this one. It's too good to be true." Most people didn't quite believe all this. So, but anyway, so actually in that lecture, I actually also recorded. If you want to take it, it's actually I put this number over there. I said, "Well, I don't know whether we can believe it or not, but this is just a wonderful number over here." And then it turned out that the following year, all the computer vision group actually not only duplicate results, but also improve that better, including our Microsoft research group. So we are actually latecomer in the sense. Okay, but anyway, so this is that particular year. Just one single year, it makes a huge impact in image recognition. And I think University of Toronto took all the credit for this. And so this number is a shallow model, somewhere around here. And just the first year of deep learning, it dropped error down to about 15%. Now the second year, that includes New York University, and also include quite a number of companies, including Microsoft. They all participate in this competition. The best result is about 11%. It dropped error down a little bit more. Now this year, 2004, the result was, that's about three or 4 months ago, last October, when the result was announced, the error dropped down to 6.6% by Google. So they put the best people there, and they, build up the network up to about 20-some layers with the parameters. And without parameters, it's about 60 layers. And a lot of parameters you don't train. So between 20 to 60 layers, and it's just getting bigger and bigger and deeper. And the error is down to about 6.6%. And then our Microsoft have a very, very nice group in Beijing, Microsoft Research in Beijing. About February 5th this year, that was about 3 months after the competition result, they published a paper dropping error down to 4.89%. So this is, so this is right here, this paper by our colleagues in Microsoft Research in Asia. This is the date. Okay, and this is just wonderful result. So this is a number down here, and this is a number from Google computation. Yes.
Image
1,000.
That's the number of nodes?
No, that's the number of classes at the output. Yeah, how many categories you can assign to the image. Okay, so this number, and then I think one day after this number was publicized, there was a huge media coverage. And then the title of the media coverage says that now Microsoft beat Google. And then the day after that, there was Google published paper in the same. These are no peer review people, just archive. And the media coverage also came back, and because Google also immediately published paper not completely written. Okay, I think they look at this, and then they reported 4.8%. And then the media title is that now Google regains the. It's very interesting. Everything happened about within 1 month. Within 1.5 months ago. But anyway, this is a very, very interesting competition. That's the end of image. Okay. Yes.
What's the method for classification? In other words, you're saying there's.
Oh, that's very simple. So you build layer by layer representation, not.
The classification is, but how are they building those layers? In other words, how are they building the classifiers in an automated way, or is it still?
Everything is automated. The whole point of deep learning is that you have what's an algorithm called backpropagation. It actually gives end-to-end learning. You actually provide the target at the top layer, and then the learning goes all the way to the bottom with the raw feature.
Structure is learned, or is
No, structure is not learned. Correct. No, structure has to be built simply. So image, if you just directly use deep neural network for image, it's not going to work well. You have to use the convolution structure, and that structure, is well known. Okay, so next. So this is actually, my time is almost up. This is actually just much introduction to everything. Okay, so the real work that was done after all this was done by what's called semantic modeling, and that's getting much more interesting now. And I think Microsoft is really taking the lead in this area. Although our company don't actually have a lot of publicity outside, because a lot of work, has interesting, value to Microsoft. So we do publish some of the work. So I'm not going to talk detail about all the business implication of this, just to tell you what kind of technology we have, developed. You can imagine what kind of business application you might have. Okay. So we have, for that reason, in order to do this kind of modeling, we established this technology center. So I'm actually, managing the researchers and developers doing, a whole bunch of applications you're going to see down the road. Okay, next 20 minutes. Okay, so what the model we built is called Deep Structured Semantic Model, DSSM. So think about this one as the deep semantic model. Okay. So we do have a whole bunch of publications here. I'm going to talk strictly from publication over here. Okay, so I actually at the end I do have a list of publications. If you want to know more detail, you can see that. And of course, application we don't talk too much, but I'm going to give a little bit hint as to what kind of application we have been doing. So I'm not going to go through technical detail, except to let you know that Okay, so the whole point, I should say that. So when you talk about semantic model, that means you have the sentence coming in there. If you have business activity coming in there, what is the underlying semantics? What does it mean? Okay, if you know what it means, you can do a lot of things, right? For email analysis, for web search, for advertisement, all these things can be done if you understand what the information meant by computer. Okay. And that's what's called, so the meaning, extracted meaning enabled by this model is what's called the semantic model. So the whole point of this model is that let's see, there are a few sort of technical points here. So it's that we train this model using various signals. I'm going to show you what kind of signal it is. That signal comes from different applications. But most of them, we acquire the signal without human labeling effort. Otherwise, it's too expensive. Okay. So, for example, one of these type of signals that doesn't require human labeling is the click signal for Bing. We have to have Bing in our company, right? So every time you search on the Bing or Google, if you search Google, Google got your signal. Right? They use that to do whatever they do. Now, if you use the Bing, Microsoft has that signal, and we use that signal. You actually donate that signal to Microsoft, to Google. So you don't think that you got a benefit. You donate other things to them, and then it actually tells you that information from this to this is related, and that's extremely valuable signal. And you don't have to pay any money to get it for the company viewpoint, and we take advantage of that signal. So I'm going to show you some examples here. So I'll show you. So rather than giving you all the mathematical description of this model, I'm going to show you an animation to show you exactly how this model works, and then I'm going to show you a whole bunch of applications for this model. So suppose you have a phrase called a racing car. Okay, so you have to understand what's the meaning of a racing car. Right? So it's a car, or it's used for racing. Okay, but when you put together, how does computer know what it means? Right? So the way we do is that we build neural network, deep neural, many layers, matrix, nonlinearity, and then at the end you get 300 dimensional vector. Okay, so that vector, you don't know anything about it, right? So you do, so in the beginning you randomize everything here, you code this in terms of whatever symbol. You code that in the symbol. Coding information in the symbol is very simple. You just look at the dictionary. The semantic meaning doesn't get captured when you do this. Though when you just multiply them all, so if you don't train all these parameters, there's no meaning extracted. They're just random numbers. So when you initialize them, you do this. You get this vector, 300-dimensional vector, arbitrary. Okay. So racing car give you this vector. Now you get something of Formula 1. Are they related to each other? Okay, they're related to each other. Although there's nothing in common with the words, right? If you use a symbol, nothing in common, you don't learn anything. Okay. Now if you do deep learning, you come up with the connection. I'll show you how it is. So, but during model installation, nothing is going to happen, right? This is random. So this one can be here, it can be here. They don't have to be the same, right? Even if the meaning is the same. Now, when you get another one called racing towards me, for example, okay, it's random as well. So it has the same word, racing. Are they related to each other? Not really, right? Even if the words are the same, they don't mean the same thing at all, right? These two are very similar to each other in the concept, but they don't have some word in common. So if you use a symbol to code the information, like most of natural language processing people are doing, you really don't learn much about their connection. Right? Okay, so that's initialization. Nothing is learned here. Now, the next step is the training. So this is the learning process, and that really is the secret sauce of how everything works. So in the learning process, we compute what's called cosine similarity between semantic vectors. Okay, so when you initialize this, this goes to here, this goes to here. They are random, right? They are not the same, right? Even if the meaning are the similar, and these two are random as well. Now, when we learn, the weights in the deep neural network, what we did is that, okay, sorry. So when we learn the semantic vector, we actually know that when user click put this racing car, Formula 1 website may show up and people get clicked. We know that. So if we know that they are related to each other. Therefore, during the learning process, we force the cosine distance between this and this to be small. Okay, we make the distance to be as small as possible, and that's the objective function. And since this almost never get clicked when user use a racing car, then we want to make them as far apart. So we want this to be close to each other. We want this to be apart from each other. So we develop this formula. It's an objective function saying that if they're close to each other, positive example, we want the numerator to be big. Okay, that means cosine to be small. Okay, cosine this to be small, and then everything else we want to be big. So numerator being small, denominator to be big. So numerators are the ones that has a click information. That means that computer knows that they're close to each other, and those which are not click, we make that to be denominator, make them larger as well. So when you take the ratio between the two, you optimize them. You force that to be close to each other. You force them to be far apart to each other. Okay, and then you do backpropagation. And that's how backpropagation. And this I don't have time to go through all detail or algorithm for those of you who know. Now, after everything trained, then you do the same thing again. See the racing car, whatever it is. Now these are already trained, are learned. Once they are learned, Formula 1, wow, the same. You know why the same? Because during the training we force them to do the same. Okay, so they are similar. Okay, therefore you can actually rank them. So racing towards me, when we train them, make them apart, as much apart from each other. Therefore, you have many other documents you can do. You can use cosine distance to rank documents for a specific query. Therefore, when you type in something in the network, the right page will show up, even if the right page has no similar words to you. Right? It's a very intuitive idea, and we use that as the basis for many applications.
I'm sorry, can I ask, are you actively forcing those apart, or just bringing those together and they
Both.
have to go
Yeah.
apart?
So if you optimize that cosine of the ratio, you do both.
Okay.
Yeah, they do both. Okay, so I'm not going to go. Well, except that this all is done by GPU. Okay, so this is just example for web search, right? So there are so many other things we have done. Question answering, it can be done this way. Automatic application recommendation can be done this way. Natural user interface can be done this way. A whole bunch of things can be done this way. Our center explore many all these applications. I'm not going to go through all the detail, except we actually publish a lot of them. But usually we don't publish it in the big file. We publish in the small ones, so people don't notice them. Right? But now I said that, people you can notice that. But anyway, so I'm going to show you two examples, given the limited amount of time. One is automatic image captioning. Okay, so that's a very interesting task. Right? So not only you recognize the image, you want let me go through. So image captioning simply means that if you have the image here, and then what you want to say is that people, when you have the image here, you want people to write down a sentence. Right? People will write down a stop sign at the intersection of the city street. Right? So it's not recognition task anymore. Right? It's called captioning generation. It tells the story of an image, of a video, or if whatever, a movie or something.
Self-driving cars will need these.
Yeah, eventually it might. So I'm not going to go through. So the model that I showed you earlier actually was used in this system. And again, we actually published this paper in CVPR. We have about 10 people working together on this in the summer with 4 interns. We've worked hard on this. And Google at the same time has the paper on this, and then Stanford has the paper there. So that paper submission was about 2 months ago. And then the minute they submitted, they call New York Times, and then New York Times, put the paper, published a big paper about their work on weekend. And we saw that, wow, we should have called them otherwise. So we called them too on the Monday. They said, that's old news already. But anyway, but all these papers got accepted, 6 papers got accepted, because the 6 groups are doing simultaneously. Stanford has the paper, Toronto has the paper, Microsoft has the paper. And it's a big race out here. Everybody, and they don't even, this is supposed to be, typically people go to academic, CVPR, ICV, they wait until conference coming here. No, they only publish it in this open source. And then they call media, and media cover them. It's kind of very strange world now. And all because deep learning. Without deep learning, people wouldn't do that. But anyway, I'll show you. But I don't want to go through all the here, except to share some result. Well, okay. Yeah, so all these are. But this is the most interesting result to show that. So this is the photo. And then you ask machine to describe what they are. A machine will say a group of motorcycles parked next to a motorcycle. It's okay, not too bad. And this is a human neighbor. Human neighbor said 2 girls wearing a short skirt, wearing short skirt, and one of them sitting on the mic. And do you know why? Other people say, well, machines don't care about girls. And then for other examples, we get some very interesting results. So of course, if you compare this to this, do you prefer this or do you prefer this one? Maybe you prefer this one. Huh? Some people will prefer this one. Some people say equally well. So we actually did crowdsourcing, to ask people. I don't have to go through it here. And then about 23% of the people on the Amazon, on the Mechanical Turk, say that machine is as good or better than human annotation. So example that I gave you, maybe it's equally good. Well, maybe maybe not. So a majority of them still prefer humans. So we're getting there. Right? So next year we probably expect this number to be 35%. The following year maybe 50%, and then you see what I'm saying? Yeah. So I think this technology is getting very quick.
Can you distinguish the
can you?
machine from the human? If you give them.
Yeah. So if I don't tell you this machine is human, are you able to tell which one do you prefer? Well, I don't know.
I wouldn't tell you.
Okay, if you can tell that you belong to this, okay, that's not bad. But how about the other one? Yeah. So for this picture, which one do you say? A woman in a kitchen preparing food. Woman working on counter near kitchen, sinking, preparing food. Maybe similar, huh? Yeah, that could be similar. Well, anyway, so we choose good examples here, but there are a lot of bad examples, and that's why it's only 23%. So that's you get a gist of what's going on here. So now I'm going to get the next example here, and this example is a real example in Microsoft Office. We released that. There's an article written about this. I would like to tell you about what it is. So this is called the contextual entity search. How do you search? So I'm going to show some very good example. I would like you to go home to try. So I'm promoting Microsoft product using deep learning technology, and that's called the article. This Microsoft published that. So it's called the Bing brings the world knowledge straight to you with insight for Office. And the underlying technology is called the machine learned relevant model. Is actually empowered by deep learning. Our group actually contribute to this. So I'll show you how it works. Okay. So if you open up Microsoft Word, okay, and your kid probably is writing some article, right? And he will say Lincoln was 16th president of the United States, and he was born in I forgot. He want to write essay. Normally, do you know what you do? Typically, you go to Wikipedia, right? You type in, you can even type in Lincoln, right? If you type in Lincoln, movie may show up, right? You have to say Abraham Lincoln, and then you get the information. You have copy back here. Now for this Office Insight, this is a new feature from the Office. You don't have to do anything. You just right-click here on Lincoln, And then this will show up right inside, right in your Microsoft Word. And then you just look at it, you copy the answer back here. But how does it know it's Lincoln? It's not. So the movie Lincoln won't show up. The car company called Lincoln won't show up. And the town in Nebraska won't show up. Right? You know why? If you just put Lincoln there in your Wikipedia, in your web, all three may be there. Right? You probably have to choose one or the other. It's not, because our deep learning takes into account the context. So if you click over here, automatically Microsoft Word look at surrounding. It sees that, oh, they talk about United States of America. It has to be Lincoln, not the other Lincoln. Okay, and that provides a lot of convenience. So that is going to make using Microsoft Office more productive, and that's the kind of productivity. It's just one single example of how this deep semantic model is working. Okay, and the reason why it's got deep.
It's not going to show up as Abe Lincoln. It can be anything, right? I need some context to it.
Yeah. So the context is here. It's automatic. Yeah, exactly. So the whole point of this work is that the X and Y, semantic model, we use this to condition on this when we train that cosine distance. Therefore, if you see something like this will be close to each other. Therefore, this Lincoln will show up because in the training, similar conditions will put together. Yes.
Question. Is this just implemented in Office 365, so it's got
No,
cloud behind it?
it's only in Office. It's only Word Online. It's not everything. So
What I mean is, it's online, meaning Office 365. That's where you've got the cloud behind it.
Correct.
It's not running on your
correct.
PC.
That's correct. It has to be in cloud. Otherwise, you don't do all the deep learning computation. That's a good point. But 365 hasn't put that in yet. So correct.
I expect they will.
It will.
And now I know what insight will mean when I see it.
Yeah, exactly. Yeah, so keep that in mind. So when Microsoft announced, but it actually was announced in a just small version of Microsoft Word.
Speed to run it?
Uh-huh.
Is it super fast? I mean,
Yeah, it's super fast. You don't notice any difference.
Okay.
So I'll show you some negative example for deep learning. Yeah, for this cloud, I probably want to, if I talk with the expert, I show a lot of negative examples so people know that I'm not talking about flowers only. I'm also talking about some negative. So one negative example is called the malware classification. So for this example, when we have different neural network, we don't really, gain very much, and then we understand why. I mean, most people don't. Most people doing deep learning think about it as a black box, right? So since you have gone through so many examples, you really know what tasks will be good for what kind of model, and the reason why this is very difficult to improve using more depth. It's really because the data that we got is actually adversarial in nature. So we actually published a paper on this about 2 years ago on this negative example. But the result is still good. A neural net is just one single layer neural net is as good as multiple layer. And in the past, people have very hard time understanding why, because the more layer you get, the better arrangement you can get. Now for speech, for language, for image, these are all true. Now for some data, it may not be true. So just I'll let you know that not everything is good for deep learning. And then if you want to know why, you have to do, to really have good scientific training to understand why, and all experience. So this the same task that we fail using deep learning now become a standard task in Kaggle. Anybody know Kaggle computation? Okay, you know Kaggle computation, okay? And then now this year we actually put this task over there. So I heard about. Anybody know about this competition? Okay, so can you say a few words? How many group participated in this?
This, I did that sea plankton thing which came up just before this.
Okay.
I did that. So I haven't yet started doing this.
Okay. So the result that we published 2 years ago may be verified or maybe disproved by this competition. And that competition has how many days to go? 40-some days to go. So usually it's the same thing, right? Everybody put, typically people get about 100, 200 groups submitting them. The winner will get $12,000 or something. But you have to put all the source for them. This is a company. They actually collect all the data, the source. And the president of the company from about last year, in the previous years, last year quit that to be president of it and having started company doing deep learning, because in the past, deep learning had, under his leadership, Kaggle actually has so many competitions. Always, he told me that, in most of the tasks, deep learning won. And he wanted to do it by himself rather than letting other people do it. So he got this small company doing, and he's now a founder of this company. So we're going to see the result for this mail. But I would expect that deep learning probably won't be the top one. well, if it's consistent with our result. So the summary is that after this talk, I'm going to finish that very soon. So Microsoft actually started this deep learning about 2009. Now we invented this type of DNA model in 2010, and it revolutionized entire speech recognition industry. From the 20-year-old system to the new deep learning system, now universally adopted by both industry and academic, and then everybody know in this. And then Microsoft created the first success example of deep learning at industry scale. Now, deep learning is very effective now, not only for speech recognition, but also for speech translation. Microsoft did tremendous amount of work on this. And also image recognition, and this now is in image tagging for OneDrive, Microsoft. And we are late to start this, as I showed you earlier, but we caught up pretty quickly. And image captioning, the one I showed you, that hasn't gone to any product yet. Someday, you're going to see that. It's coming soon, maybe not. I don't know whether Microsoft will be the first one to come up, probably not. And the language understanding, I showed you a little bit of this, semantic modeling. And I didn't have time to talk about all this, and some of those I'm probably not feel comfortable talking about. Use a whole bunch of things. And the enabling factors for all this success is that we have big data set for training deep model, and we also have very powerful general purpose GPU computing. That's very important. Otherwise, we couldn't even run all these experiments. And the final important factor that many people ignore in this community is that we do have a huge amount of innovation in deep learning architecture and algorithms. So a lot, in the beginning, we got a comment, somebody saying that, well, is neural network the only architecture around? If it is, then there's not much innovation, right? Architecture is fixed. Now, to do the kind of things, semantic modeling architecture are so varied, and a lot of innovation actually coming into how to design the architecture based upon the design, the deep learning principle, and also your understanding of the domain problem in order to design the architecture to make that effective. So there's a huge innovation opportunity here, and the innovation, at least from Microsoft research standpoint, is on how to discover some distant supervision signal which are free from human labeling. If you require human labeling, too expensive. It's just not going to scale up. Okay. So like web search example I show you, no human, right? Automatic user, you gave the signal to us and we use it. Okay. If you don't give us, it's not going to succeed. And how to build, and after we understand how to get this supervision signal, then we need to know how to build deep learning systems grounded on exploiting such smart signal around. And the example will be DSSM I showed you earlier. Now, I think that's pretty much. Now, another summary. Yeah, this summary actually is written for experts on speech, on deep learning. Okay, so for speech recognition, I would say I'm very confident to say all low-hanging fruit are taken, no more. Okay, so you have to work very hard to get any gain. And so for that reason, my colleague and I, we wrote a book, about 400 pages book summarizing why this is the case. And people have to work very hard to do that. So it's good to get out to get other, faster progress on. So every time you go to the conference, a lot of work that you see, beautiful piece of work, they don't get as much gain. It's a tiny bit of gain, much more work. Not like 3 or 4 years ago, just one GPU, dump in there, a lot of data, doing a little bit innovation in the training, you get a huge amount of gain. Well, now the gain becomes smaller. This is not to discourage people from working on this one. This is actually to encourage serious researchers and undergraduate students who want to write PhD thesis to get into this area. So low-hanging fruit, and for startup company, don't do that. Okay, if you do that, unless you find some good application to use technology, not the technology by itself. Now, for image recognition, I would say most of the low-hanging fruit are taken. Right? So now it's getting, the error rate just dropped down to 4.some%. It's almost the same as human capability. So if you get more data, you get more computing power, you can still get error down a little bit more, not much more anymore. Now, for natural language, I don't think there are many low-hanging fruit there. Everybody has to work very hard to get the gain, okay? Including all the deep learning researchers. Now, for business data analytics, that's a new research frontier. Some low-hanging fruit there. I'm not going to say too much about this. Now, also for small data, many people think that deep learning may not work well, and that's wrong. Okay, many people always say that for small data, use traditional learning method. Don't use deep learning. Big data, use deep learning. That's wrong. And there are so many examples for Kaggle. And as well, we're going to hire somebody who actually won that competition, to join our group to do this. So deep learning may still win. Okay, it's not guaranteed. For big data, for perceptual data, especially it's big. Deep learning always win and win big. Okay.
Perceptual meaning
Speech, image, human sensory, and then maybe gesture, maybe touch, that kind of things. I think deep learning will get. I have some theory as to why that happened. It's partially because if you look at the existing human system, it can do better. The neural network really simulate many of the properties of this. There's no reason not to do well, right? And now be careful. If the data has adversarial nature, or if data has some very odd variability, which I don't have to go through yet, we have tried some failure example. Be very careful, okay? It may win or may not win. So for those of you who are interested in this kind of problem, security problem, pay attention to the new Kaggle competition. When they come out, you probably get better. If I could be wrong, okay? So I'm actually curious. I work on this with some very strong people on that. We haven't got any gain. And if anybody gets some better result, that will be very interesting. I could be wrong. I'm very open to admit, but so far I'm not wrong yet. That's before that competition result came out. Now, issues for near future deep learning. This is my last slide. Now, for perceptual tasks that I showed you earlier, speech, image, video, gesture, etc. Now, the issue here, okay, this is a very important issue. Everybody in this community asked that question. None of those has answers. I'm just throwing out to you to make you think. And these are all the issues. I myself think a lot about this. And I'm looking, every time I go to a conference, I look for some answers, whether they address any issues. They address this issue, it will be interesting. It could be surprising. So with the supervised data, like speech has all the supervised data, image has a lot of supervised data. The issue is that what will be the limit for the growing accuracy with respect to increasing amount of label data? So far, it hasn't reached the limit. Speech kind of reached the limit. We can see that if you get more data, you don't get as much gain. Now for image, we haven't seen the limit yet. You get more data, you still can get better result. Okay, so we don't know where the limit is. Okay. Now once we get the limit, then we want to ask a question beyond this limit, or when the label data, which are typically very expensive, to collect, if the collecting more and more data become non-economical from company viewpoint, then will novel and effective unsupervised machine learning emerge, and what will they look like? Whether it's deep generative model or some other kind of model. And many people actually are working on it from academic viewpoint. So when you go to academic conference, you look at people doing unsupervised learning, generative model, don't throw them away. Although they haven't seen any great result compared with the supervised learning, the one I showed you earlier. So I always, every time I go to conference, I go to this session. I don't go to whatever session that I know about, and because they might show some good result after the limit is reached, and the limit probably will be reached within 2 or 3 years of time, and that's my expectation. Now for cognitive tasks, including natural language, reasoning, knowledge, which I show you a little bit about natural language, the issue is that whether supervised learning, like machine translation, for example, beat the non-deep learning state-of-the-art system like speech and image recognition. Okay, so far machine translation, there's a beautiful piece of work coming out from Google just about 2 months ago from this conference called NIPS 3 months ago. It's just beautiful piece of. They match the best result for the competition. They haven't got a chance to beat them yet. So every time we get together, for a conference, they keep telling me that they got a better result. I never trust that. But so far, it hasn't shown that it's beating that. So we don't know whether it will actually do as well, because this is an easier task than this. Right? The cognitive is the higher level of the brain activity, and this is the lower level of brain activity. Now, and then another issue is how to distill the distant supervision signal for supervised deep learning. So the example is that DSSM, we already got many low-hanging fruit. Okay, and what is the best way to exploit distill information? Like web search will belong to this kind of class problem, right? And then you have to think hard how to get that information into your system. And I give you example DSM how to explore that information. And this is low-hanging fruit, right? Once you realize that clear information will help you to increase your numerator and decrease your denominator, you learn how to do that, then you get all the the bang out of everything. That's a very easy problem. And as a matter of fact, our deep learning engine are pretty much the same. We just get different supervision signal. We get different. We actually get different the objective function. We optimize in the same way. And the next question is that, well, dense, whether the dense vector embedding, which I showed you earlier, I didn't use that word, the embedding. The embedding is that you get all the symbol, you embed them into a vector, low-dimensional vector. So whether the vector embedding with the distributed representation, whether they will be sufficient for a language problem, okay? I personally believe, based upon some of the literature that I have seen, it could be quite likely to be yes. But that dimension has to be very big. And the alternative question will be whether we need to directly encode or decode the syntactic semantic structure in the language. Like up until about 6 months ago, my feeling is yes. We need to have somehow to be able to recover the structure so that you can do reasoning. And after I read all this Google's paper, Facebook, wrote, a few just beautiful set of paper, we haven't got a chance to do research in this area.
Your language translation has to do that, for example.
No. No.
You don't have to recover the semantics and then reconvert them?
No, just the recurrent network that will just speed up all this information out. And that's the one that I mentioned. This is just amazing. The first time we read the paper, we thought, that's too good to be true. It turned out to be true. But anyway, these are the set of questions. Now, for big data analytic tasks, which I don't have time to, I'm not going to go through all the detail, is that with the question is that whether vector embedding is sufficient, just like in language. It's not clear yet, okay? Should the embedding method to be different from those for language? It's not clear. What are the right distance supervision signal to exploit for this kind of task? We don't know. Whether there's also data privacy issue, or whether we need to to do all this kind of analysis, embedding, encryption here. That basically deep learning has when I say near future, I mean 2 or 3 years from now, people will go through all these issues. I expect half of these questions will be answered within the next 2 or 3 years. So that's the end of my talk. So I give you, so this is open. I'm ready to answer any question. I'll give you some selected publications from our group and from Microsoft. Partner. And this is the only selected group over here, selected publication over here. Thank you very much. Yeah, question.
In one of the slides where you showed the deep neural network architecture, its dimensionality is actually continuously decreasing from 100 million to 500K.
Correct.
So it's always decreasing.
Correct.
From my experience with some image classification work, like the first layer, if we do an expansion,
Okay.
and then go down,
That might work. That would be called, it's called the bottleneck feature, right? But for text, for image, that may be true. That may be true. But
I've
if you
seen
read this,
better results with that.
but if you read, but if you read this recent competition, the paper by Google, by our Microsoft Asia people, it's just standard convolution network. You do convolution, you do pooling, you do convolution, and then pooling again. Which
I think the same effects could possibly be replicated by 2 layers where you kind of project up and then go down.
Yeah, I don't believe so. I think because this task has been done by how many, dozens of groups. They have been doing that for since 2012, for 3 years. I have never seen any architecture looking like what you talk about.
Okay.
So I think what you want to do is that you actually want to try your architecture on one of the ImageNet tasks. If it actually give you better result, I think you'll be very famous.
Okay.
Yes.
What is the prospect on a regression type problem? All the things that you mentioned are more classification type.
Classification.
More regression type problem.
Regression problem. So actually, the ranking problem, the DSSM that I talk about, actually is a ranking problem. It's not really regression. It's called a ranking problem. Now, for regression problem, this one is just as good. So it's like the only difference to be made is that the upper layer, rather than being softmax, you simply just mean square error.
But are there any dramatically good results like?
Well, but so far we don't have any computational result for regression. Right? Okay. If there were, I'm sure you will beat them. Yeah.
So convolutional neural networks, it needs a lot of data. So what's a lower bound of the data? Like how many images?
Okay, so for ImageNet, it's about 1.2 million images, which is considerably big before. But for speech, it's very small. Right? Speech, we use about the data that most of people use. It's up to about 500 million samples in terms of frames. And that's the average, the big system that we have seen. Now for 1 million, but there are some other tasks with more data. So actually the more the better, but the whole point is that up at about 1.2 million for image, deep learning already showed dramatic advantage. So I expect that the limit is lower than 1 million. Okay, and then in some of the tasks that I show you gaggle competition for the chemical or drug discovery task, the number is only about 40,000 or something, and they got better than anything else. So, but they have to do a lot more work. How to regularize? You have a lot of data, you have to do more work. You have a lot of data, machine does more work.
So just one general question. For the training, my understanding, suppose for image, for object, it can be rotation, scaling, translation, distortion, all kinds of stuff. For speech, can be different dialogue or different noise or those kind. How can we know when the model is overfitted or for example, is?
I know. Yeah, so the convolution, for example, in image, only deal with the shift invariant. Right? Yeah. And that's good. But you're talking about there are so many other things, and that's why you have many of what's called feature maps, not just one single map. If you have one single feature map, you only can deal with one type of distortion. You have many, typically you get about how many? 20 to 200, somewhere around that. So for different feature map, you will hope that different map, because you initialize them differently, they will capture different kind of variability. And that's probably the right answer to you. So variability, the overfitting. So so if you have lots of data, overfitting may not be the problem, right? If you have small amount of data, overfitting, becomes serious. And there are many techniques developed in deep learning community that solve that overfitting problem, like drop out technique. If you have small amount of data, always use drop out. If you have small amount of data, always use pre-training. Right? So those are called, deep belief network, also called the restricted Boltzmann numbers, using those kind of models to initialize them. Therefore, you actually have, partially solve the overfitting problem. Then when you do backpropagation, you tend to have less overfitting problem. That will be the right answer.
Okay, thank you.
We have last one.
Question?
Go ahead.
Yeah. So you mentioned GPUs as being kind of one of the enabling factors. And clearly for training, there's been, some huge resources thrown at these problems. But one of the other trends is we're seeing, companies like NVIDIA put more GPU technology in portable devices. And I'm just wondering, how does that play out? Do our portable devices end up doing the classification, doing the speech recognition, or do we always have to maintain connections to larger clouds? So does GPU power in a portable device bias?
No. So most of the things actually are like this about voice search. So the information, all the computing is done in the cloud. So the result gets transferred back. So within this device, you really don't have to put all those things. But there are also, I have seen a lot of startup companies in speech recognition, especially in China. They actually built the embedded deep learning model in here. And that requires, and they lose some accuracy. But as long as they find the right application scenario, losing some accuracy is okay. So I think there's a big balance between the two. But in US, most of devices they have seen actually use cloud.
But looking forward, do you see that shifting? Or?
I don't see in this country. No, I really don't see, because so far transmission is just so low, right? The bandwidth is large enough, I think.
And we'll have 5G in a few years.
Yeah. So I personally don't see that. Yeah.
Okay, thank you very much.